Okay, so I'm going to be making my own toolchain for my own programming language, and I'm going to start by emitting 64-bit machine code. So I've got the Intel Software Developers Manual here, and I just wanted to give a quick, rough overview of how encoding for various instructions works. So Volume 2A, Chapter 2 says, this chapter describes the instruction format for all Intel 64 and IA32 processors, where IA32 is the 32-bit architecture and Intel 64 is the 64-bit architecture. The instruction format for protected mode, real address mode, and virtual x86 mode is described in section 2.1, and increments provided for IA32E mode and its submodes are described in section 2.2. So if we go to, for example, Volume 1, Chapter 3, which is Basic Execution Environment, we get this quick overview of modes of operation, where in IA32 architecture, we get protected mode, real address mode, and system management mode. And then within protected mode, there's virtual x86 mode. AMD groups all of these under a top-level legacy mode, or at least that's what they call it. So these are basically sub-modes of legacy mode. And then Intel 64 architecture introduces this IA32E mode, which AMD calls long mode. And IA32E runs in one of two submodes, compatibility mode or 64-bit mode. So back to the instruction format. In order to encode various instructions, you basically just follow the format that's laid out in this diagram here. So you'll start with any optional instruction prefixes. For example, 66 is the instruction prefix to override the operand size. So if you're running in a mode where 32-bit operands are the default, then prepending it with a 66 will make it switch to 16 bits. If you're running in a mode where 16 bits is the default, then prepending with 66 would make it switch to 32 bits. That's then followed by an opcode, which can be 1, 2, or 3 bytes in length. And then if required, you follow that with a ModRM, which is how you select the two operands for instructions. And then if you need to use a scale, an index, or a base register, you add this extra SIB byte as well. Displacement is displacement for memory accesses, and then the immediate is the literal that's embedded in the instruction itself. So the ModRM and SIB bytes are both broken up into these subfields. They both follow the same format of being 2 bits, 3 bits, and 3 bits. And the mod here is used to select, for example, memory access or register access for the RM field. So this RM field here can be either a register selection or memory access through a register. And this mod is how you choose whether it's direct register access or memory access through a register. This reg opcode field is always a register or an opcode extension. And then if you need an index base register or scale, you would add the SIB byte which has the scale. This scale can be 1, 2, 4, or 8. Index is how you select the index register, and base is how you select the base register. So each of these selection fields has 3 bits in it, which means that you can encode the index 0 to 7. And IA32 architecture gives you the registers AX, CX, DX, BX, SP, BP, SI, and DI. And these are numbered 0, 1, 2, 3, 4, 5, 6, and 7. So for example, if you wanted to use the reg field to encode access to the CX register, you would encode that as 001. That would be index 1, which would point at the CX register. So looking down here at opcodes, they use this terminology primary opcode, which can be 1, 2, or 3 bytes in length. And if we look down a bit further, they give a longer example here. So for example, for this instruction, they give the example of the sequence 66-0F3801. This 66 is not the operand size override prefix. This is actually just a mandatory prefix for this particular instruction. So these 3 bytes here are the primary opcode. And the terminology here is a little bit confusing. If you cut off this final byte here, this is actually the opcode. And then these 2 bytes here are selecting an opcode map. So if we go down to volume 2D appendix A, we can see this section that talks about opcode maps and how to use them to decode bytes and figure out what instructions are being encoded. If we go further down, we can see a table. So this is the 1 byte opcode map. So if you have a primary opcode that is a single byte, you can use this table to decode the instruction. So for example, the opcode byte, or one of the opcode bytes for the MOV instruction is 89. So if we go down a bit further, we can look for 89 in the table, which comes down to this particular encoding of the MOV instruction. But if they want to reuse this 89 with a different interpretation, that's what the opcode maps are for. So an 89 just on its own uses this single 1 byte opcode map, which AMD calls a primary opcode map. If you prepend the opcode with this 0f, this is the escape byte. And the escape byte selects what AMD call the secondary opcode map. So if we go down a bit further, we can see that there are these tables where they say that the first byte is 0f. So this is the 2 bytes or secondary opcode map. So if we look for the same 89 in these tables, which is down here, we can see 89 is this particular encoding for a conditional jump instruction. So 89 on its own using the primary opcode map is a MOV, whereas if you use the escape byte to select the secondary opcode map and then use 89, this is actually a conditional jump with this encoding here. So there are 2 more opcode maps. You can see that there's a table here that says that the first 2 bytes are 0f38, and then there's 1 more opcode map down here, which is 0f3a. So out of all of these, you can basically have nothing before the opcode, and then just the opcode on its own. This is the primary opcode map. 0f is the secondary opcode map. Then there are 2 more opcode maps, 0f38 and 0f3a. So if we look down a bit further, we can see this table which just describes how all of the bits come together to form a ModRM byte, which is how you select the 2 operands for instructions. The top 2 bits are the mod, the bottom 3 bits are the RM field, so this means it can select a register or memory access through a register. And then the middle 3 bits are just a register selection. And those combine together to make a single ModRM byte. This is the 16-bit table, so we'll skip this one. This is 32 bits, which also applies to 64 bits. If you need to encode the reg field, so you want to encode modrm.reg, that is this row along the top here. RM is this column down here, and then mod is this column down here. So if mod is 0, 0, 0, 1, or 1, 0, these all correspond to different memory accesses, which you can tell by the square brackets here. The only difference being really that the 2 here have a displacement added to the end. So this one is an 8-bit displacement, and this one is a 32-bit displacement. This one is no displacement. The other thing to note about this is that this hyphen notation here means that you have to follow with a SIB byte. So if you need to use a scale index or base register, then you must select one of these hyphen rows here, depending on which one you choose depends on whether you want a displacement or not. So for example, if you wanted to use a scale index base with no displacement, you would select mod 0, 0, and then you'd make sure to set RM to 1, 0, 0. The other thing here is that this DISP32 in 64-bit mode is actually how you encode RIP relative addressing. And then finally, this mod11 here says that you're using the RM field to select just a direct register. So this table here is the same sort of table, but for the SIB byte instead. And it's the same idea. The top row is how you select the base. This is how you select the index, and this is how you select the scale. The scale includes the ability to encode the fact that you have no scale, in which case you would choose one of these none rows here. And if you have no base, you would choose this asterisk field here. And at the bottom there's a note about the asterisk, which is that if mod, for example, is 00, then you have to put a DISP32 after the SIB. So what this means is that, for example, in the ModRM table, these hyphen entries are where you would usually find the SP register, or if it was 64 bits, this would also be the same sort of encoding here for using R12. So because you can't encode SP or R12 directly using this row, it means that you have to encode those as a base register in a SIB byte instead. And this DISP32 here is where the BP or R13 selection would be. And because this is DISP32, this is RIP relative addressing, in order to use one of these two registers, you're forced to actually use this BP encoding here or here. So if you have no displacement, you would choose this one to make sure that you only put 1 byte of 0 displacement instead of 4 bytes of 0 displacement after the instruction. There are similar limitations in the SIB byte. For example, if you want no scaled index, each of these none rows here are where the SP register would go. This means that SP cannot be used as a scaled index register, so that's one limitation. You can use R12 though. So R12 is available as a scaled index, but SP is not. This is where BP would go as well, so this is obviously meaning no base, but there are ways that you can encode all of these things, which we'll look at a bit later. So moving on to VEX prefixes, this is where they talk about 64-bit mode. So in IA32E or long mode, there is 64-bit sub mode, and 64-bit sub mode adds these VEX prefixes. And VEX prefixes allow you to access the extended general purpose registers and SSE registers, and they allow you to set a 64-bit operand size. So even when running in 64-bit mode, 32-bit operands are usually the default unless an instruction would implicitly be using 64-bit anyway. So here is the same diagram again, but they've just added the VEX prefix before the opcode. And if we go down a bit further, there's a table that shows how the VEX prefix works. So the VEX prefix always starts with a 0100, which is a 4, and then it's followed by a lower nibble which encodes these 4 flags here. So if you want to specify a 64-bit operand size, then it means that you need to prepend the opcode with a VEX prefix with the W bit set. So for example, if you were accessing EAX from the ModRM bytes, but you actually wanted to access RAX, you would need a VEX prefix where you set the W bit to say that you want 64-bit operands, and that would be accessing the RAX instead. Similarly, if you want to access extended registers R8 to R15, then you also need a VEX prefix because these bits here extend the fields in the ModRM and SIB bytes. So in the ModRM and SIB bytes, you get 3 bits of information, which allows you to encode from 0 to 7, which is registers AX to DI. But if you want to access R8 to R15, then you need at least 4 bits of information. So that's where the VEX prefix comes in. If you want to access, for example, R8 from the reg field, you would set the reg to 000, and then you would add a VEX prefix here with the R bit set, and those would combine together in the way you can see in the diagram here to give you 1000, which is 8, and that gives you the R8 index. So the R always extends the ModRM reg field, the X always extends the SIB index field, and then B changes depending on what you're doing. It's either the ModRM RM field, or the SIB base field, or the Opcode reg field. There's just more diagrams here showing how the VEX prefix extends different fields depending on what you're doing. Then there's this table of special cases for VEX encodings to sort of take into account when you're writing something like an encoder. I'm not sure why this is a question mark here. I think it's supposed to be a not equal sign. So 1, for the mod means that you're saying that the RM field is selecting a direct register. So if mod is not equal to 1, then it means that the RM field is selecting memory access. So this B star here means that you don't care about what the value of VEX B is for this particular special case. So in the case that RM is 100, which would be the SP register selection, that is where you get the -- row. And so in that case, as I said earlier, that means that you have to follow with a SIB byte, which means that a SIB byte is required for SP-based memory addressing. And then here are some 64-bit implications, which is that even if VEX B is set, we don't care about it. In that case, you also require a SIB for R12, because ESP would be 100 for the RM, and then if you added the VEX prefix, that would be extended to 1100, which would be 12, so that gives you R12. So because they are both selecting the -- row, it means that you have to follow with a SIB byte, which means that you have to select memory access with both of these registers by using the base register instead. And then there are just more things to think about here. So for example, this is where it's saying that SP cannot be used as an index register, but here it's explicitly saying that it's 0100, which means that an index of 1100, which would be R12, is actually allowed. So RIP relative addressing, that's just the DISP32 row that I pointed out earlier. Here's a table describing the same thing. So if you've got mod 00 RM 101, this would select the DISP32 row in the ModRM table. And then it's just saying that in 64-bit mode, that actually becomes RIP relative addressing. And if you want the same behavior as compatibility mode, you then need to do this encoding here, which is to use a SIB byte instead. So that's sort of one family of encoding, which they refer to as legacy encoding. So legacy encoding is how you encode instructions like MOV, add, sub, compare, things like that, you know, like SSE instructions. Then they move on to this AVEX, so advanced vector extensions. And with AVEX, they came up with a different instruction format, which are based on these VEX prefixes. So you have legacy encodings, then you have these VEX encodings, and then later with AVX 512, they added EVEX encoding as well. So there are sort of these three different families. They're very similar to each other, but it's just the prefix bytes change a little bit. So here we can see the layout of the instruction encoding bytes. So similar to the legacy encoding, there's still an opcode, a ModRM, a SIB, a DISP, and an immediate. These all work exactly the same as they did before. The difference here is that they now have this 2 or 3 bytes VEX prefix. So you no longer have a dedicated REX prefix byte, for example. That's all been collapsed and compressed down into this VEX prefix instead. Or, for example, we saw the example instruction where they had the 66 mandatory prefix for one of the SSE instructions. That has also been collapsed down into the VEX prefix. So if we go down a little bit further, we can see the layout of the bits. So there are two types of VEX prefix. There's a 3-byte one and a 2-byte one. And which one you use just depends on which features you need. So for example, you can see here that all of the REX prefix stuff has been compacted down into this VEX prefix, but the 2-byte one only provides you with rex.r. If you needed rex.x or b, you would have to use the 3-byte VEX prefix. If you also needed to set the opcode map to a specific one, then you would need the 3-byte prefix, or if you needed to set the W bit, you would also need the 3-byte prefix. Otherwise, you can just get away with using the 2-byte VEX prefix instead. So a couple of new things here is that you get the L bit, which lets you select between 128 and 256 vector length. So that's, whether you're using XMM or YMM. The VEX prefixes also allow you to select a third operand, which is described by this VVVV subfield here. With the ModRM and the SIB bytes, they only contain 3-bit fields for selecting an operand, which is why you need the REX prefix extensions. But with the VEX prefix, they already give you 4 bits immediately, so you don't need an extension to encode these ones. You already get access to the extended registers here. Okay, and then the other thing to notice about this is that the 3-byte VEX always starts with a C4, and the 2-byte VEX always starts with a C5. Okay, so after VEX prefixes, they then go on to this other family of encoding, which is the AVX 512 encoding. So this uses an EVEX prefix, which always starts with 62. And that's then followed by 3 bytes of information about the encoding. They also, so the same as legacy and VEX, they have opcode, RM, SIB, DISP, and immediate, but they also add this compressed 8-bit displacement that's scaled by this N. Other than that, it's basically the same thing. There's just a few more flags that you can set. So for example, one of the things that EVEX gives you is the ability to access 32 registers, so you can access 0 to 31. And this, for example, could be ZMM 0 to 31. In that case, you would combine, for example, the ModRM field with the REX prefix extension, and then they also give you another extension. So here, for example, there's the REX prefix R, and then there's an EVEX R prime to give you 5 bits of information to encode all of these register indices. The VVVV field is still here with 4 bits, and then you get this V prime to extend that. And then I think it's the X one, the X bit extends the final operand. You then also get this AAA here, which is how you select the K registers. So for example, if you want to select K0 to K7, you encode that in this AAA field. And if you want the K registers to be zeroing masks, you would set this Z bit to 1 or 0. L is also still here, which gives you 128 or 256, but then there's also L prime, which lets you go to 512 vector length. This is also overloaded to do some other stuff like SAE and things like that. So if we go down a bit further, there's a table here that just describes how all of the different fields are used. So for example, here this is vector length or RC. This one is 0 or merging. This one is, broadcast. RC, SAE, context, for example. So some of these bits are sort of overloaded a bit depending on what instruction you're trying to encode. So if we just have a quick look at an example of an instruction, so MOV is a common instruction. So here it tells you the opcode that you need to use, and then there's this notation here, which in this case is /r. These notations are described in Volume 2A, Chapter 3, Interpreting the Instruction Reference Pages. So here, for example, you can see that /r means that the ModRM byte contains a register operand and an RM operand. So if we go back to MOV, you can also see that the operands are placed according to which field would encode which operand. So the RM field encodes the destination in this case, and then the reg field encodes the source in this case. And then this is just 8-bit, 16-bit, 32-bit, and 64-bit. You can see here that this MOV actually has the same sort of form, but they've just been, the operands have been switched around. So in this case, if you're doing register to register, either of these forms would do the same thing. You know, this form and this form would do exactly the same thing. But as soon as you need memory access, that's when this ordering becomes more important, because RM is the only operand the only field that can encode memory access. And so if you need memory access in the destination position, you would make sure to choose one of these forms. One of these forms here. And if you needed memory access in the source operand, you would make sure to choose one of these forms here. For the 64-bit version, you can see they tell you that you need to use a VEX prefix with the W-bit set, and then you follow that with the opcode 89. And then for the byte MOVs, you get this completely separate opcode. And that's because, for example, if you want to do a 32-bit MOV in 64-bit mode, that would just be, well, 32 bits is the default operand size anyway. So let's say we wanted to do this MOV here as 32 bits, you would literally just put 89 and then follow it with your ModRM and SIB bytes or whatever you need. If you wanted to switch that to 16 bits, you would prepend the operand size override prefix. So if you do 6689, this would be the same 89 opcode, but it would select the 16-bit one instead. And then to do the 64-bit one, you would prepend with a VEX prefix, which is 4, and then the W-bit set makes it 8, and then you would follow that with an 89 to do the 64-bit operands. So because there's no way to encode a byte operand size just based on like prefixes and things, they give you a completely separate opcode to do the byte ones, which is 88 instead. So if we, for example, try and do an encoding of this by hand, so we'll create a test.asm file. It's going to be 64-bit, and we'll do a MOV, let's say we'll do a MOV to some memory location, which we'll do as a base register of RAX, plus the scaled index of RCX multiplied by 2, and we'll just say there's no displacement here. Then we'll move from the register RDX. So if we were going to encode this by hand, we know, for example, that we need to use 64-bit operands because we're using R as the register. So RDX is the 64-bit register. We know that there's a memory access, and we know that we're using a base register and a scale register and a scale. So we need a SIB byte, which means we know that we need to select the -- row. And we know that the displacement is 0, so the -- row that we select will be the one without any displacement. So to do the 64-bit operand size, we need a VEX prefix, which always starts with a 4, and then the W-bit being set is 8, so we get the 4, and then the W-bit being set gives us 8, so we have 48 as the VEX prefix. Then we have 89 because we've got the memory access is in the destination position, which means that we need to choose one where the RM is in the destination position, which is the 89 opcode here. So we would put 89 immediately following the VEX prefix. Then we need to choose our ModRM. So if we go back up to the ModRM byte table, So we know, for example, that the reg field is in the source position, and that's going to be dx, which is 0, 1, 0. Then we know that we need this hyphen hyphen to specify a SIB byte because we're using a scale index base. So that would be 0, 0 for the mod, and it would be 1, 0, 0 for the RM. And these all combine to make, you do the mod one first, then you do the reg, which is 0, 1, 0, and then you do the RM, which is 1, 0, 0. So in this case, this is 1, 4. And if we follow that across to the cell, we can see that it is 1, 4. So the mod RM byte is 1, 4, and then because we selected the hyphen row here, that means that we need to follow with a SIB byte. So for the SIB byte, we know that the base is going to be AX, and we know that the index is going to be CX multiplied by 2, which is this one. So SS has to be 0, 1, and then the index field has to be 0, 0, 1. So these combine a bit differently. In the mod RM, you would encode it as this one, then this one, then this one. But in SIB, you encode it as this one, then this one, then this one. So we'll do 0, 1 as the SS, then 0, 0, 1 as the index, and then 0, 0, 0 as the base. So this gives us 8 here and 4 here, and if we follow that across to the cell, that's what we get, is 4, 8. So the SIB here will be 4, 8. So now if we go and just assemble this with NASM, and then just go open up the binary and switch to viewing hex, we can see that there is the VEX prefix 48, followed by the opcode 89, followed by the mod RM 14, followed by the SIB 48, which is exactly what we said it would be. So going back to the instructions, if we just have a look at one more instruction, which is ADDPS, you can see in this case, this is an instruction that contains all 3 encoding families. So this SSE one here is just the legacy encoding family. These AVEX ones here are the VEX prefix encodings. And then these AVEX 512 ones are the EVEX encodings. So in the case of legacy, you would select the secondary opcode map with 0F and follow it with the opcode 58. And then the R meaning that you select both of these operands with the ModRM bytes. If you wanted one of these two with the extra operand, you would use a VEX prefix. This is telling you what the length bit should be set to. This is telling you what the opcode map bits should be set to. WIG means that it ignores the W bits, and then you follow that with the opcode, and then again the ModRM. The ModRM selects the RM field and the register field. And then this additional operand here is just selected as the VVVV field in the VEX prefix. Then with EVEX, it's more of the same, except that you get an extra length of 512 down here. In this case, it's saying to set W to 0, follow that with the opcode, use the ModRM and the VVVV fields. You can also select the K registers and choose whether they're zeroing in this case. And that's about it, really. The op-n column here contains A, B, and C, and these correspond to these columns down here. So it's saying that in the A encoding, operand 1 is the ModRM reg field, and that's a read and a write. Operand 2 is the RM field, which is a read. And then in the other two cases, B and C, it says that the operand 1 is the ModRM reg field, operand 3 is the RM field, and then operand 2 is this VVVV field instead.